Excellent. I think we're live. Howdy. Okay, so we're ready for electron configuration. Let's do an oversimplified look at quantum mechanics. This is not going to be going into math, a whole lot of math on this. It's not even really what I would call a great model. It's a good one to get a basic concept. So, don't get into an argument with a nuclear physicist over anything I tell you. Here we go. All right, so we're going to start off with a picture of Bohr's model. So here's basically Bohr's. Oh, hang on, move my Earl Grey. So Bohr's model of an atom. We've got the nucleus in the middle. We've got he called these distinct energy levels. He numbered them one coming out. All right. We can go up to 7, but the model actually works even if we go bigger. And so let's see, in the PowerPoints, I go through our frog jumping. Basically, the electrons are like my frog and they're going to jump. They can't stop in between the energy levels, only on the energy levels. And then the real important thing is what happens when the frog jumps back. All right. So I'll let you look through that. I'll be going through a bunch of these terms. All right. And so let's just kind of throw out a whole bunch of terms at us. So we've got our electrons. They start off in the ground state. And remember, the protons have a positive charge, electrons have a negative charge. They want to be close as they can to each other. The protons are in the nucleus, so the ground state for the electrons, where they're all as close to the nucleus as possible. That does not mean that they're all in this first energy level. Matter of fact, that first energy level can only hold 2. All right. And so as we get further out, there's more space, and the electrons can hold more. Now, Bohr's model, I'll just tell you right now, works great for hydrogen. Did not work for helium. But let's play with his model because we still use a lot of his terms. All right, so electron spins around and it goes from the ground state. It absorbs energy. It gets excited. So excitation, absorption, and it moves to a higher energy level. Now, it can only absorb certain quantum of energy. It can only absorb certain packets. In other words, it has either enough to get to 3 or it stops at 2. And if it has more than enough to get 3 but not enough to get to 4, it'll stop at 3. There's only certain places it can be. And then once it's there, it's in the excited state and it'll relax back down to the ground state. Now, it actually just wants to get back closer to the nucleus. So that doesn't mean it necessarily does it all at once. It could just go back down to the next energy level. And so each one of these, as the electron relaxes back down, it releases that energy, and it happens to release it as visible light. And so we see that as colors for many of these transitions, and so we see the visible light. Now, this is why certain elements glow when they are in fire or when we apply electricity to them. All right, so you get them hot and they glow because the electrons are being pushed out and then they relax back down. It's a really pretty quick process. All right, so excited state, relaxing back down. Let's see, what else do we got? A photon is a packet of that light. So a photon. All right, so when I want some tea, all I have here is my packets. So I've got a packet here of Earl Grey, and I want, let's say I want 2 bags of tea. I have to open 2 bags. If I want a bag and a half, it's not going to work. I still got to open 2 of these containers. All right, and so it's a whole number of these quantums. So when the light's given off, it's a photon of energy. And we can actually calculate that energy based off of these transitions. How far did it travel? What's its energy? What visible light would it be? Okay. All kinds of great stuff there. So let me scroll down here. And so we get, let's see if there's any more definitions we got here. Ground state, excited state emission, quantum, photon. Looks like we got it. Okay. All right. Now the problem with Bohr's model, it works great for hydrogen, terrible for helium. We fixed it, terrible for lithium. All right. So we had to get to the Heisenberg uncertainty principle. So let's look at those pretty pictures here. Stolen right out of Pearson. Oh, man. All right. So they've got these orbitals here. But here's Heisenberg's uncertainty principle. Now, I am not by any means going to show you the math behind it. You want to learn this the proper way, then please continue with your math. Take some calculus, take some differential equations, come back, examine this. And don't let me tell you that this is all 100% correct based off of the math. I mean, some of the best scientists in the world argued about this. There's still some debate over, is this right? Well, I'm slowly tilting. Oh, well, we'll deal with it. Luckily that's my camera and not the RV. All right. So anyway, Heisenberg's uncertainty. I'm not even going to use all his symbols. He said there's some level of uncertainty. I was reading up on this today. He didn't even call it uncertainty except in the footnotes. Just that's what caught on. Now, he said that the reason why we can't really predict where these electrons are going, and it's because now we base it off of, we expect it's because the electron and electron impulsions. They don't want to be close. But what he actually said, that there's some level of uncertainty in the position, uncertainty in the position. So I'm going to put a lowercase u and a p, all right, times the mass plus the uncertainty, another lowercase u, whatever. We're not going to use the symbols. Don't worry about it. Times its movement or its energy. All right. So we'll call it its movement. All right. So, well too many M's. How about its, so we got position and, we call it velocity or something. All right. But it's not really just velocity. It includes its direction. So here's the problem. What this is actually saying is there's some minimum level of uncertainty in every measurement in the universe. But this kind of goes against what we would know. We would have come across this before. Why are we suddenly not able to do these very good? And it really comes down to when we're young, we learn to catch a ball. We learn to catch, hang on. We learn to catch, to monitor where our friends are. We do. Right. And so you don't have to, when if I throw a ball against the wall, I don't have to worry about throwing the ball and it bounce it back, throwing the ball, it bounce it back, and then sometimes being on the other side of the wall. It didn't go through the wall, it's just on the other side of the wall. I don't ever have to worry about throwing the ball and it was here and then it spontaneously goes over there. It's never in two places at once. It doesn't do a lot of the weird stuff that some of these electrons do. I usually give the example that when you're driving in your car, and the other car, there's another car on the road with you, and they're 3 lanes over, and they do not instantaneously leave that position and be in your lane. And my wife tells me that kind of stuff happens all the damn time when she's driving. I don't know, but I think that's something else going on. But with Heisenberg, what he's saying here is that this uncertainty is in everything. And the reason why we didn't see this before was because that mass more than takes up for it. So when I come back and look at this mass usually more than covers this level of uncertainty. All right. Oh, wait. My face is going. All right. I'm back. Yay. All right. So usually this uncertainty more than covers the mass. But for an electron, remember we're talking 0.00054 AMU. Whoa. All right. Really, really small mass. You round it to 0. It has a mass. You can treat it as a particle. What we end up here is really struggling with an electron. And so what he's saying is you got to look at it as a wave, not just a particle, but you also then have some level of uncertainty. All right. So what does this mean for us? So I want you to know in the term Heisenberg uncertainty principle, you cannot know the exact position of an electron and its motion at the same time. One or the other, or a little fuzziness in both. All right. Okay. So for us, what it means is we don't have to worry about doing the math, right? Because the math is no longer algebra based. It's now going to be calculus based. It's going to be based on statistics. It's based off of where are we likely to find an electron. And so we call these orbitals. All right. Now we could do the calculus on it. It's a Hamilton and Schrodinger equation. And oh, man, there's a lot of famous people. A lot of really interesting math. Once you get to that level, go back and revisit. It's really cool. But we're not going to hit it. All right. What do we need to take from this? This is defined as 90% likely to find an electron. 90%. The other 10%, that's where some really cool stuff happens. All right. So we start off, we describe kind of a sphere, and that's our first basic orbital. And, when I look over here at this rough thing, there's your sphere. Now, what we want to keep in mind is there's 0 chance of finding the electron in the nucleus. All right. And there's only certain places it's going to be, but there's a little fuzziness in the math on the inside part. So there's a little bit of a distribution, a chance it could be on the inside. So it's another layer on the inside that's real thin. All right. And so the math is not described best by sphere. So it takes care of most of it, not all of it. So we'll see that come back and bite us. That's actually going to cause, we'll call it electron tunneling. All right. Now there's other ways of looking at this. If I do a cross section of where I'm likely to find the electrons, so if I move out this way, all right, so I'm going to have a little blip and then a big blip. This is where the electrons are supposed to be, but there's a little bit of a chance to find one there. Okay. All right. So electrons, these orbitals, let's look at a nice pretty drawing of them. I'm not even sure where I stole this one. Anyway, we got a sphere. Oop, can't see it over there. A sphere. We've got these other shapes. Let's see, it's originally named after the signals from radar. So you got some kind of sharp and some kind of peak and who knows, and I don't care. We now know this SPDF. So let's get this SPDF in that order. All right. Then we're going to go GH. I think it's I, and then J gets skipped because it's not in every alphabet. So look, we ran out of space on. All right. But alphabetical after that, repeat if we needed to. I mean, and when we get down there to AA, it's fine. All right. The math on this is really cool. When you solve the equation, you get back the original equation plus an answer. You solve it with that answer, you get the original part back and a new answer. And you can keep going. It just gets more and more complex. So the spheres are, this S, we usually just refer to as a sphere. The S does not mean sphere, but it's a great way of remembering it. The P, most students say that's a peanut. Kind of has 2 distinct lobes. Now, usually they're shaded a little bit different. All right. One is mathematically a plus and one is a minus. For everything that we do this semester, we'll consider those to be the same. You get into a little more advanced chemistry, you may have to worry about it. Not so much for here. All right. D, I used to struggle with what do you call this shape? All right. It's kind of 4 lobes, right? There's 2 positives and 2 negatives, and Whoa, I don't know what's going on. So 4 out of the 5 are these weird shapes. Okay. So student much smarter than me at one point told me that was a double peanut. Oh, I can't make a U today. A double peanut. And so a double peanut, that's open a bag of peanuts. Those are those peanuts that have grown together. It's a genetic mutation. Usually, genetic mutations. That means don't eat those, or I recommend save them up, eat them all at once. Eat all those peanuts at once. See if you can get superpowers or something. I don't know. All right, so then F, then most people say that's a flower. It's got a lot of different petals in it. But man, what I'm going to take from this picture. So I'm looking over here at this picture, and I've got a couple of different things here. So I've got one S kind of orbital. So let's make this like a handy little table to summarize some of the basics here. So we have S, P, D, F, and G, H. All right, and we can take it as far as we want. So now these we'll talk a little bit later about. It's got a lowercase l. These are the numbers. We'll actually these are actually defined, and we'll talk about this L here in a little bit. But this is 0, 1, 2, 3, 4, 5, and we're just gonna go numerically as we go. All right, up by 1. Now, how many orbitals are there for the S's? Well, when I come over and I'm looking at my S's, there's just 1. And how many for the P's? Well, there's 1, 2, 3 pictures. So when I summarize this data, I've got 1 S, 3 P's. If I count the D's, I'd have 5 pictures. Oh, now I start to see the pattern. Odd numbers, 7, 9, 11, and so on, if I need to keep going. Now, one of the things that we want to know about these is each one of these orbitals, one orbital holds 2 electrons max. One orbital holds 2 electrons max. So, doesn't mean it's always going to hold 2. But now, there's other things that we describe on this, all kinds of different things. So, let's start with just the basics here of a real nice, simple picture. The electrons, they move around here. And if I imagine this spin is actual movement in a clockwise and a counterclockwise direction, it's actually more to do with the way the electron is actually spinning itself as it goes around. Don't worry about it. So clockwise, counterclockwise. Let's say it's going this way, and there's another electron we're going to add. Now there's 2 ways we can add it. Okay. Oh man, you know that no good boyfriend of yours? Everybody seems to have one. No good ex-girlfriend. I don't care. It's just that one that you really hate to see. And you're going to pass them on the road. And as you pass them, there's 2 ways you can do that. You can drive by and you can go, boom, oh, there's that no good. Ooh, ooh. Or you can be stuck going in lane next to you. You're going at the same speed. Oh no, you're stuck in traffic right next to each other. And you just got, ooh, which one is more repulsive? Well, that's what we got to think about for these electrons. Remember, they have the same charge. They don't want to be close. And so if I have one going clockwise and I add another one in, it can go counterclockwise. So they just kind of zip past each other. It's okay. And then if I add a third one in, though, it would have to go the same direction as one of the other 2. There's only 2 options, a clockwise and a counterclockwise. So that's why each one of these pictures can only hold 2. That means the S's, there's only 2 that can fit in there. The P's, 2 can fit in this picture, 2 in this picture, and 2 in this picture. That would be 6. So when I come back over to my chart, we said the S's can hold the number of electrons. S's can hold 2, the P's can hold 6, the D's can hold 10, F's can hold 14, G's 18, and 22, and so on. And we keep carrying that out. Okay. Now, really kind of going on. Let's expand out just a little bit. These are really looking at what we call quantum numbers. And if I just briefly touch on this, N is telling me the distance. That goes back to Bohr's model. How far out are we from the nucleus? What layer are we on? L then tells me the shape. Am I looking at an S, a P, a D, an F, so on? All right. Now, each one of those had different ones. So M tells me the orientation. Now, that's not super great. But when I come over here, you see these -1, 0, +1, -2. All right. That's where those kind of come from. Those are the values for M. So if I know that it's -1, it's this picture. And if it's 0, it's here. So what relationship do those have? Well, it's actually easier to think about those. You've got one going across this way, and then one coming straight up and down, and then one going across that way. So they're 90 degrees to each other. Nice and easy to figure out. All right, and then D's gets a little more advanced. And so there's just ways. What are we really looking at? We're looking at different answers to our calculus. All right, now S, we'll think of it as the spin. And it's either +1/2 or -1/2. In other words, there's only two directions. Now, we had the Heisenberg uncertainty principle. Let's see. Let's get the how about the Pauli exclusion principle? All right, and it says no two electrons in one atom can have the same four quantum numbers. Man, that sounds great. All right, Pauli exclusion principle. It said we're going to take, if you have four quantum numbers, it's exactly one. If you have three, then it tells you which orbital you're in, which specific orbital you're in, and there's only two electrons that could possibly be in it. All right. And then if I come up to L, well, I know that S's hold 2 a max, and P, there's 3 different ones. So there's 6. All right. And D's hold 10, and so on. And if I do N, then we can play with these numbers. But what this really does is even easier than that we have, we'll learn to show this 1s, but we get the first energy level only has enough space for the s. And then as we, just like when you order a medium pizza, it's a lot bigger than a small pizza. And when you get that large, its diameter might not be much bigger, but it's a lot bigger. All right. So when we go out in energy level, we add a new orbital. All right. Yeah. So every time I go down a row, I'm going to add a column. 3p, 3d. All right, so when I get to 4s and 4p and 4d and 4f, and oh no, this stuff is all on the test if you wanted. It's on the back of my periodic tables, but I'll show you. You don't need to memorize all this. All right, we just want to know, hey, there's no such thing as two d's. There's no such thing as the four f's. I mean the three f's, right? And so as we go down, what happens when we get to the 5s and the 5p and the 5d, the 5f, and we predict the next one be 5g out here. Okay. Now, Pauli exclusion principle tells me a limit of how many I can put in each one of these. Okay. Remember, all the S's hold 2, all the P's can hold up to 6, the D's can hold up to 10, the F's can hold up to 14. Okay. All right. The stuff going on. So when I get to describing these, we're going to use a little bit of different types of language here. We're going to use electron configuration, and then later we'll talk a little bit about electron diagrams. They're not overly difficult. So electron configuration looks something like this. And it's a nice way of summarizing what we would get if we use the quantum numbers. Now, I'm not going to give you the rules for these quantum numbers just yet. Let's just give you an example. N equal to 1, L equal to 0, M equal to 0, S equals to 1/2, N equal to 1, L equal to 0, M equal to 0, S equal minus 1/2, N equal to 2, L equal to 0, M equal to 0, S equals to 1/2. And see how they can have the same four numbers, but some of the numbers can repeat. All right, so N equal to 2, L equal to 0, M equal to 0, S equals negative 1/2. Let's see, N equal to 2, L equal to 1. I've used my 2 there, so now I got to go to this shape. M equals negative 1, S equal to 1/2. Oh, man, we're getting, let's see, then I would do N equal to 2, L equal to 1, M equal to negative 1, S equal to negative 1/2, N equal to 2, L equal to 1, M equal to 0, S equal to 1/2, and we'll get to it in a minute when I make some of these choices. N equal to 2, L equal to 1, M equal to positive 1, S equals 1/2. You'll notice I didn't go in maybe the order you expected. Some other stuff comes in. But whoa, this is a lot of data. This is telling me here's one electron and it's here. Here's another electron. It's here. So what is this telling me? Well, if I try to tell you where my car is, all right. So I'm going to tell you, I say, hey, go grab something out of my car for me. Would you? Here's the keys. You're going to say, where are you parked, Dr. J? Well, I might have to tell you, what row am I in? Or what parking lot am I in? Where do you even start? A lot of parking lots on campus. Okay. Then you're going to need to know which row I'm in. Okay. And then when you go down the row, they're not really numbered. So when you're walking down that row, you've got the left hand side and the right hand side. You kind of need to know that so you know kind of which way you're checking. When people do rows, when they're driving, they don't really think about that. They think about the driving part of the row. All right. So if I were drawing a picture of a parking lot, you would say, "Oh, the row is where the cars are." But when you're driving, the row is where the cars aren't. All right. And so anyway, you're driving or you're walking out there, and you got to know which side way to look and how many spaces down. And when you get there, if I've given you all four of those pieces of information, you'll know where my car is. There won't be any other cars there. We're not going to have any kind of. There's never two cars in the same spot. All right. Sometimes you get one car that seems to take up two spots, but all right. That information is okay, but you don't want all that information. If you see me and I'm walking out of the parking lot and you're like, "Hey, Doc J, do you see any spots?" And I say, "Yes." Well, the first row, the first spot had a car in it, and the first row, the second spot had a car in it, and the first row, the third spot had a car in it. It's not going to take long for you to just drive off. All right. So what electron configurations are for is to give us a nice sense of what's filled, what's not. All right. So this one is telling me N is equal to 1. All right. That's the first energy level. The S tells me L is equal to 0. That's when we had to know those numbers. So it's telling me L is equal to 0. In other words, it's shaped like a sphere. Why didn't they just do this? Because it would look like 10 squared. And then the 2 up top is telling me the number of electrons. Now, that is not super helpful unless you know how many are in each possibility. So this is saying this has 2. As long as I know the S's can hold 2, this one's full. This one, the S's are full. The P's are not. They're not full. All right. So, not too difficult. These are really pretty straightforward. All right. Now, if I wanted to draw these as pictures, energy would go this way. In other words, we get further away from the nucleus. We would get the 1s, and it's, imagine a little box, I guess, and it would hold 2 electrons. Now, typically in an energy diagram, So then we'd have the 2s, and then we'd have the 2p, and there's 3 orbitals, and they're all the same energy, right? They're the same distance. And so when we put these in, we're making these, we're going to add, there's our symbol for an electron. It's got 1 barb. And so we might say that this is 1/2, and this one is minus 1/2. Here's what we're going to do. Remember, you can't have the same 4 quantum numbers. So if I put this first one in going up, the second one has to go down. This is called an electron diagram. All right. So think about this as the quantum numbers are like the parts list when you open up an IKEA bookshelf. All right. And then you might have written out instructions, and that would be the electron configurations. But the diagram, the picture, shows you how it's all kind of put together. And then you can pick up a lot more information at a quick glance without having to try and think things through real critically. So I can look at this, quickly see, hey, this one's filled up like that. And then I made some choices, and the choices that I made when I filled it up the last time was actually I came here, and then here, then here, and then I came back and put one in going down. So I did one going the same way each one. All right. That is an application of Hund's rule. All right. And so it says when they're the same energy, each one gets 1 before any of them get 2. All right. So if I have, they're all gonna, and that there's something special about them all being half full. But when we get them, they all get 1. Ooh, let's do Hund's rule. I call this my guy code. This is, I don't mean to be sexist with it, but it's something that just you run into all the time. Girls, you ever wonder why your man might when he's parking the car might leave a spot between him and the other car? He might say it's because of trying to keep his car from getting dinged up, but it's really the guy code. All right, and we learn this at a young age in urinals. That's where we learn it. You don't want to stand right next to people. You want to leave every other one, or there's actually an order of filling it. So let's look at, okay, so I've got a badass TV, and I have 3 couches, and I bought them at the same time. They're all identical. Excellent. All right. And I'm going to have some of my buddies come over, and we're going to watch a football game. All right. So we go off to the kitchen. We're eating, getting snacks, getting drinks, and we're going to come in here and sit on the couches. Now, buddies, we're big old boys. So only 2 of us fit on one of these couches. It's just it take up a lot of space. Now the first guy, he comes in. It does not matter where he sits at all. So let's put him over here. Okay, so he's over here. He's all happy. Now the next guy can come in. He has a lot of choices, but not all the choices. Can't sit where this guy's already sitting. And then according to the guy code, he really shouldn't sit here. We're close buddies, but it's just not really acceptable to sit there. He could sit way over here. That'd be fine, but it seems like a little rude. So what he's going to do, he's going to sit here. Right? He's not too close. They're spread out, okay? But he can sit here, and he can put his drink here, and he can talk to this guy real easily. Next guy says, oh, man, I'm going to sit right here so I can join the conversation. And so that's really the only place left for him to sit. He could sit over here, but it doesn't flow as well. It's just more work. It's easier if he sits here, he can talk to everybody, no problem. All right. Now the next guy comes in. There's 3 spots left. It totally doesn't matter where he sits. Totally doesn't matter. All right. And then next guy comes in. Doesn't matter. And then the last guy sits there. So what we did is we put 1 on each couch before any couch got another one. Hund's rule also says that if you start off up, all these other 2 will be up. That they're going to be going the same direction. All right. All right. Woo. A lot of stuff going on there. How do we get these electron configurations? Well, you would think you're going to add in for S, for P, 4D would be next, for F, 5S, and 5P, 6D, 6F, and 6G. All right, you would keep it going down. We can do it infinitely. You would think I'd fill up the 1S, then I'd go to the 2S, then I'd go to the 2P, then I'd go to the 3S, and I'd go to the 3P, and the 3, and left and right. That's what would make sense to us. I totally agree. But remember this whole idea of electron tunneling, that inside part of the s orbitals. So when I come back over here, let's see if I have a nice pretty picture of my, we don't need any of that. Here's our pretty picture. What we actually find is if I took this next step up, 1s, 2s, here's my 2s, my 2p's, the 3s the next, then the 3p's, but the 4s is actually lower in energy than the 3d, even though the 4s is further out. It's a whole nother layer out. Why is it lower in energy? It's got that inside. The s's are unexpectedly stable because it's got that inside probability. All right, there's a little bit chance that it can get a little bit closer, and it lowers the overall. Man, we do some neat stuff with that. How I'm going to do that here? Then I need to predict this, that the 4s comes before the 3d. So here's the way that people usually do this. Now we're not going to use this a lot. I'll provide this for you if you want, but I'm just going to draw these arrows. I'm going right to left. I'm going to try and keep them parallel. I'm going diagonal like this. So that would go through my 6s, right? And so on. Now the way you read this, and many of you probably learned this, you would start here at the 1s, you'd fill it, and you wrap around and come up here. And when you fall off, you come back to the next one, and the next one, and then you're just going across. A lot of people come in here and they put a 2, and a 6, and a 10, and a 14. All right, and so on. You do all that. Easy and stuff. No problem. So how does using this work? This is the way that I don't like to do it, but I'm going to show you now so I don't have to teach it in class. Oh man, I had a young lady that asked me one time, if I know how to do this, why do I have to learn it the other way? And my answer to her was, this is like riding a bicycle. It'll get you there eventually. But nobody really likes doing this. They like to do the Ferrari method. So this bicycle method is based off of 3 questions over and over and over. First question is, what's next? You're going to follow this path. Second question, how many does it hold? That's here. And the third question, how many do I have? All right. So I'm going to start with, so let me grab us a periodic table. This one's got all kinds of stuff on it. Let's see if I can find a better one. There we go. So I'm going to come over here. I'm going to pick an element, and we're going to start with a neutral one. So we'll do nitrogen. It has 7. Okay. So nitrogen has 7. Let's jump down over here. And so I've got 7 electrons for my nitrogen. It's got 7 protons. We're going to assume it has 7 electrons. All right. 7 electrons. First up is 1s. It holds 2. Do I have 2? Yes, I got 7. So I put my 2 in here. I got 5 left. All right, next up would be 2s. It holds 2. I've got 5. I put my 2 in here. I got 3 left. Next up would be, after I fall off there, would be the 2p. It holds 6. I don't have 6. I only have 3, so I put my 3 in. Okay, that works okay. Ooh, hope you freeze framed. Oh man, let's do chlorine. 17. Are you kidding me? All right, 1s. It holds 2. I have 2. I got 15 left. Then the 2s. It holds 2. I got 2. I put them in. I got 13 left. Then the 2p. It holds 6. I got 6. I put them in. I got 7 left. Then the 3s, it holds 2. I've got 7. I got 2. All right. Then after that, I'm going to be the 3p. It holds 6. Oh, I only got 5. I put my 5 in. 1s2, 2s2, 2p6, 3s2, 3p6, 3p5. Sorry. So and they should add. We started with 17. These should add up to 17. It's a good way of checking if they got it wrong. It doesn't take into account if they did the wrong directions, but hey, it's always good to eliminate. If you know you messed up, we can fix it, right? So 2 plus 2 plus 6, that's 10, 12, 15. No, 12 plus 5 is 17. Ooh. Okay, 17. Adds up. Let's do bromine. Oh, let's not. Let's not do it. Bromine. You know what? Let's learn to drive our Ferrari. So I'm looking over here at my Ferrari, and I want to do bromine. So the first step in learning to drive a Ferrari is to watch somebody else drive a Ferrari. And one of the things that I know about trying to teach somebody to drive is if you're going to teach someone to drive a Ferrari, you're going to show off just a little bit. All right. So follow along. We're trying to get to bromine right here. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. What? Wait a minute, did I do that right? Let's try that again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, 2, 3, 4, 5. Now here, bromine. This technique is based off of, I write it down for us, the off-ball principle. And it says when you move over a box on the periodic table, you're adding an electron. Move forward, just following the numbers. You move forward a box, you're adding an electron. You move back, you're subtracting an electron. Man, when I was a student, I always thought, man, that was an easy one. Not taking into account that our modern periodic table has been arranged so that this works. And so that's actually the arrangements we have here. So when I look at my periodic table, I've got distinct areas. So right up and down here, this is my first dividing line. Now notice the first row only has room for 2. That's my S's. Then over here, oh, you can't see it. So first one only has the S's. And then the rest of them, here's my S's. And they're the NS's. In other words, this is my N number. Okay. And then over on this side, here's my P's. Now remember, S's hold 2. Aha. P's hold 6. Remember? 1, 2, 3, 4, 5, 6. For every 2, I've got an orbital, so 3 orbitals. All right, so here's the P's. It's this dividing line right here. This is P's. Don't include the helium. That's the P's. All right, so NS's and the NP's. Now the D's, I need to account for the fact that we went out of order, right? So the 3 P's, then the S's, then you get the 3 D's. And so these are the 4 minus 1 D's. In other words, when I come over here, I need to account for this fact that the 3 P's, then the 4S, then the 3 D's, then the 4P, then the 5S, and right? And we'll get the 5 P's, and man, we get all this going on. So let's get a look at what's going on my periodic table and kind of summarize what I'm telling you. Here's my sections. These are the NS's. Oh, terrible. These are the NP's. Should be just a little bit higher, but whatever. Okay, so here's my N. It's my number right here. These are the N minus 1 D's. And this gives people all kinds of trouble. You literally take, if you're on the 5th row, 5 minus 1 is 4 D's. Okay? And they hold 10. Count them across. They hold 10. Then we get this box down here. And these are the N minus 2 F's. N minus 2 F's. And so to get down there, there's 14. Now here's where we run into a little trouble in our periodic table. When we get to lanthanum here, all right, notice it comes at 57, and then we drop down. So when we're filling these, we'll have the 6s, and then you might try to throw one here in the 5d1 and then drop down. This is the 4f's and the 5f's. Well, what we actually do is we fill this one, the f's, and then we catch this one on the way back. And unless we stop here, there's some weird stuff going on. Okay, there's lots of weird stuff going on in the transition elements. But here we go. We're looking at the f's. Now, there is currently an argument or a debate, I don't know, an inquiry into whether this 57 needs to be down here and 71 needs to be right here, and we need to move the split over there. That doesn't match all the experiments. And it would be easier in many ways, but then it wouldn't really match everything we see. So we got on it. We got a committee together several years ago. They're working on it. They've published, I don't know, 5 or 6 papers, maybe a lot more by now, maybe 3 books, talking about how difficult the problem is. So once they're done writing all their books, they're ready to tell us the answer, I think, right? And I'm just hoping it doesn't end up being 42. All right, so here we go. We're going to go across. Here's the way it works. We do 6s2, then we do 4f14, 5d10 to go all the way across. Then we're in the 6p's over here. Down here, I've got the 7s's. Then I would hit the 5f14. Then I'm going to do my 6d10 and then 7p6. Now, this is the last element that we have discovered so far. We're going to end up having to add an 8th row if we discover any more. So, in the 8th row, we'll have the s's. And then we're going to have, we're going to need the g's. And we're going to have to add a new box once we start discovering those. And so we'll add a new box. Remember, we already know how many's in it. We already know that these g's, and it'll be the n minus 3 g's, assuming that everything goes as predicted. Our job is to describe what happens in nature, not to tell nature what to do. That's why we have to do this math. Nature's already doing its own thing, okay? So we're going to describe what happens and predict our experiments. So n minus 3 g's, we know if the f's held 14, these are going to hold 18. All right? Because there's 9 orbitals, 2 electrons each. So you'll be able to tell your great-grandkids, oh, I remember when there were no g's on there. All right. So we'll have to end up changing it. Already our periodic table looks a lot different than this. I don't even know what year this was. This came out of our book at some point. So how did I do this? I just go and I write it down when I get to one of these dividers. So let's go up. I've got these dividers labeled here for us. So I hit one of these dividers. I write it down. So 1s2. Now, what really helps, let me go ahead. I'm going to write them down as we go across them. All right, so 1s2. Then we'd be at the 2s2. Would get me there. 2p6 will get me to neon. Right, that's all the way over here. Then I'm going to be at 3s2. And I'll have 3p6 and 4s2, 3d10. All right, so here's my 3d10. 4p6 will get me all the way over here to krypton. All right, and then here's my 5s. I have 5s2. And then we hit our 4d10. And then I'm going to have 5p6. And 6s2. Now I'm going to hit my 4f14. We'll finally get to our first f's. Then my 5d10 goes all the way across. Then I get over here to my 6p6 and 7s2, 5f14, all right, D10 and 7P6. We haven't hit any of the G's yet. So here's what I got. Here's my list as I went across all the way down. All right. All we're going to do is stop when we get to the right number of electrons. So when I do chlorine, it has 17. So I'm going to go till not quite filling up the 3P6. Always going to be in this order. If you want to practice this, you can. The hard part for most students going on right here, or this initial jump where I do 4S and then the 3Ds, then back to the 4Ps. Those are the places that give the students trouble. So we're going to read them off the periodic table. We're going to go forward. Every time I go forward a box, I'm adding an electron. All right. Now, what you could do is if you run into an atom that has positive charge, is you're going to go back a box. It's going to be isoelectronic. Electronic, if I can spell it. Isoelectronic, same electron configuration, is the box behind it. So when I'm doing fluorine, it has 9 electrons. So I could come in here and do 1s2, 2s2, 2p, 5. And then subtract 1, and I would take 1 out of this last one that I added, and that'd be 4. Or I could come in and I could go back a box. I come over here, I find my fluorine, and I go back a box to the oxygen. And when I do oxygen with the neutral charge, it's 1s2, 2p6. Whoa, what am I doing? 1s2, 2s2, 2p, and then we're going to have 4. Now, how did I get this 4? Remember, we talked about when we hit them. So I went 1s2, 2s2, 2p, and I'm going to hit this oxygen at 1, 2, 3, 4. All right, and that's how I knew where I was going. So if I'm trying to get fluorine and I'm going to go back a box, I can just do oxygen with a neutral charge. It'd be isoelectronic because fluorine with a positive charge. Remember, if I lose an electron, I get a positive charge. If I gain an electron, I'll have a negative charge. So fluorine with a negative charge would be isoelectronic with neon. Ah, well, we got a lot going on. So what are we going to do with electron configurations? Well, we'll see this isoelectronic stuff come into play. It does all kinds of neat things for us. The electron configuration controls the chemistry. And that we talked about families going up and down, and that their chemistry is very similar. Well, that's because their electron configurations are very similar. Remember, it's the outside, the outermost electrons that matter. We have a fancy word for that, the valence electrons. The outside electrons, when things bang into each other, it's the outside that affects the chemistry, okay? The outside that does the interactions. Now, not only can we predict their chemistry based off their outside, but it also controls some really neat factors. For instance, the stuff in there about iron and transition elements like copper and zinc, we get some weird stuff going there. We get some things not go the way we predict. And that has to do with a level of understanding that we don't usually give you. It really just comes into things being half full. It turns out to be almost as stable as things being completely full, or not quite as stable, but much more stable than hodgepodge. And so we sometimes leave the S half full if we can get the D's all the way full, or get the D's partly full. They're really close in energy, and so craziness. What do we care about for all this? I'm not gonna stop in the F's or the D's. I'm gonna go in the S's and the P's. I'll go all the way across the D's and the F's, but I will stop in the P's on the test. Now in class, I may ask for some examples, and if I were to ever ask you for one of these, then I'm gonna ask you what you predict it to be. All right. So if you go look up some of these on a fancy periodic table, or you go to Google and you ask, hey, Google, what's the electron configuration of some of these? Chromium will probably give you a weird one. And so it's going to tell you what it is and whether it's an exception. Now, it could make you memorize them all like I did when I was a student, and that's no fun. I'm crooked again. Oh well. So dealing with these electron configurations. Phrases First, most students eventually learn to do it the Ferrari method. You want to practice it that way. It's just a matter of learning where the S's and the NP's and the N minus 1D's and the N minus 2F's are. Learn to practice, draw them on your periodic table. So when you get on the test, if I were to give you a blank periodic table, you could draw it on there. All right. And so this is not really a skill that's overly complicated. But I've gone on for a long time about what I said was a simple model. You can do this. I think that you're going to be okay. All right. Practice it. Don't do the bicycle method too long. Do the Ferrari method. All right. So from here, we'll jump into doing a bunch more of these, but we'll play with electron configurations a little bit more in depth as we get going. So, all right.